Welcome to another stream, episode 3 of the build series, Automotive LIN Network. So we will continue where we left off, where we're designing a multi-node LIN network. It's been some days, a few days off here, but yeah, this is where we left off, multi-node network, and we're on initial design. And if you haven't been watching these episodes before, you'll see quickly how I like to work. And it's very much doing some form of system design and documentation before doing actual schematic. So doing the concept work, which we have more or less. We have decided to work only on the master in the very beginning, which includes power management, MCU, debug, a network, and a user interface. So keeping it simple in the very beginning. And down here we have, explained, short description of what this block of functionality is doing in the entire PCB. And more explanations, yada yada yada. Electrical properties, requirements. I'll just give myself a reminder, maybe in red. Reminder. Make a design template of each block, each functionality block. That I think I could be a really nice. So basically, pointing at these things here. So it would be nice to make a template of, say you're implementing a power management block. How do you do that, consistently? Because next time I'm doing a design, I might come up with a entirely different way of working, and I should standardize this. So, reminder: make a design template for each functionality block. That would mean, title, description, design considerations. For example, we must have, a block diagram, for example, is always good. Design requirements. So what requirements do we have? What is not changing whatsoever? And then these are, ways to, or in some cases, must-haves, or you get the point. Maybe selection of components. There should be a resulting documents. In the end, it should really be part of the design template, I think. You can just point it on here and write excluding. Oops. Nope, like that. Excluding. Like we don't need that, I think. But yeah, this is where we left off. So we have this power management block, which is what we started on. Looking at the schematics, we have a future connector, which we haven't chosen. Could be simple screw terminals, but now I just put it here as a future block, since I haven't decided on what type of connectors we should have. So if it's a bench power supply, for instance, we should have also some banana jacks or screw terminals could work. But then again, for the LIN communication, how should we do that? So maybe we will have some different connectors for that. So maybe power connectors and also a communication connector. So something like, what is it called? Pico blade. Something like this, Pico blade connectors. Very common. Simple. But yeah, now we're at the power management block. So we're here again. Maybe I like some colors. Oops. Need a better color here. Color picker. Something. Something like that. Just to see what we're working on. Working on power, so it has a bit of a reddish color to it. So this is where we left off. Right, we followed the typical application for this regulator, and we selected the component values. According to that, we still need to look into that though. Then we have this TVS diode, this Schottky diode, and this polyfuse, which we actually crossed out a little bit because I wasn't sure it's really needed. And trying to find one that wasn't so incredibly huge, I think, was a bit difficult. So we leave it like that. But the idea is we have the battery input, polyfuse to protect against overcurrent scenarios, Schottky diode for reverse polarity protection, and then overvoltage or more ESD protection. And then we'll have a clean 12 volt output. Clean, so we'll say clean, but in the future we'll add an EMI filter. And then it's basically the start of this regulation circuit. So first going from 12 volt to a 5-volt output. So we selected this component that has a fixed 5-volt output. +5. So there. Let's look into this data sheet again. And now we forget about everything else and we focus only on this block. So let's take the DC-DC and do that to perfection. We select the components to absolute perfection. So actually we did not finish the power management just yet. We crossed out the fuse. We did select the components, but other than that, we haven't selected anything in KiCad. So we haven't added the specific components, only generic symbols for now. So then we focus on this part right here. Let's put it here so that we can look at it like this. Okay, actually, no. Just here, put it here so I don't forget the filter to be in between here and here. Right. So this is what we're focusing on today. 12 volt, clean 12 volt to 5 volt. And we make sure that every component here is selected, at least in terms of footprints. I think we should, go that extra mile and select the actual components as well. Shouldn't be too difficult. It's just 3, 4 capacitors, or these can be the same, most likely. But 4 capacitors, 1 inductor, and 1 resistor. That's it. So it's not very complicated in that sense. So let's look at the schematic once again. We'll read through it very, very briefly. So we got 3 volt to 17 volt on the input. It supports up to 3 amps between 0.9 volt and 6 volt output. The soft start, which allows operation as either a standalone power supply or in tracking configurations. Power sequencing is also possible by configuring the enable and the open drain power good pins. So this one can be used to signal and power good of a CDC. Indicates its output voltage is stable and within the specified operating range. So this could be used to give the signal to the next regulator, for example, to start, or something else, I guess. Preventer, for example, it's crucial for ensuring downstream components receiving reliable power, preventing errors by delaying processor or peripheral power up until the DC-DC is ready, and can be used with GPIOs or LEDs to monitor power health. Right. So it got power good, power sequencing, power save mode. The devices draw quiescent current of approximately 17 microampere. Power save mode entered automatically and seamlessly if the load is small. Been a long day already. Device available in adjustable and fixed output voltage versions. Spec'd in a 16-pin quad flat on LED. No, what is it? FQN package. Very thin profile, quad flat no LED package. Very thin profile. Right. So here's a typical application schematic. Yeah, basically showing everything that we have done, except selected the switching node inductor. We can continue the sheet here. Remember, we're doing this design to perfection, or at least with high confidence. So high confidence design. Switch mode. Just connected to internal MOSFET switches. Connect an inductor between switch SW and the output capacitor. Sorry. This we don't need. It says it is recommended to connect feedback to analog ground on fixed output voltage versions for improved thermal performance, which we have done. I really want to make like I need something more to help me. And I think, let's see here now. I'll make a new spreadsheet and how to structure it. Product. No. I'll eat some grapes thinking about this. So I would like to basically, when I'm doing schematic design, it's opening up KiCad here again, taking this block, for instance, with the chip itself, and for example, in DC-DC converters, selection of components can be very important. Sometimes it's very straightforward based on different applications, I guess, and how finicky or complex you make it. So for example, selection of the inductor is important in order to set the acceptable ripple on the output. Also then the filtering of capacitors, etc. And I would just like to make a structured way to keep track of what I'm doing, so I can look back and, you know, make it simpler the next time. So let's see here. So something like this. Okay, project. Date. Designer. Don't really need that. Functionality block. Chip or IC. It has to be reusable though. So, wait, if I do like this and then put it here. So the project is the multi-node LIN Network. So in parentheses, master, since for the time being, the project is the master that we're working on. So the functionality block is the power management. The IC in question, wait a minute. Yeah, the IC is a buck converter. I can copy which chip exactly it is. maybe type DC-DC back converter date. How do we do that? Date. No. Date. Time. Date. Today? No. Today. Exactly. So again, it might feel a little bit, how to say, right? So it's a little bit like what I was talking about before with the design template, taking the most specific or the most important information and do that every time. Every time we're doing design. Power management. Pins. Package. Pin. Input. Output. Input 12 volts. Output 5 volts. I think we said 2 amps. So what package was it? So a 16 pin. So 16 pin or very thin quad flat no lead 16 pin. So what I'm doing is just creating good habits, basically. Part number. Can remove this maybe. Hey, and thank you for joining the stream. How are you? How are you? I'm just doing some electronics, all the way from concept to production. And right now I'm preparing a type of design documentation, basically. So looking at KiCad, I've selected an IC which takes a 12 volt input to a 5 volt output. And I just want to make sure that whatever I'm doing here is documented so that I create good habits and I'm able to revisit my documentation later on and see what and why did I do the different things. So for example, and here I might have to split it up a little bit. So in here I go from 1 down to, oops, 1, 2, 3, down to 16. And switch on 1, 4, power good. 5 is feedback, 6 is ground, 7 is FSW, 8 is def, SS, so soft start, and TR, not sure what TR stands for. 10 is input, and 13 is enable. So then again, it will look a little something like this. Oops. Got it. So the switching node, I will do like this. 16 pin. It doesn't really matter what the package is maybe, but it's just for now, we do it like this. Actually, I should have kept that. Pins, number, name, or abbreviation, full name, function, and then implementation. So this is what we this is what we should rename our sheet, actually. So block implementation. So I say block implementation because we're covering functionality blocks. So we're at power management. Here we have the PPS 62133, and then we can cover everything, switching node. power good, feedback. Just to remember, you know, create good habits. It's good. F switch. So now I will put this on the side. Oh, it's side here again, maybe. And we can read through here, and I will document. Switching frequency. Select. And I will also add, it's basically insert column to the left. I/O. The switching node is an output. Power good is an output. Feedback is an input. Ground, not applicable. So this is an input, the switching frequency select. Switching frequency select. Low. Right, so we pull it low to ground, which we have done, which means we set it to 2.5 megahertz. Selects. You know what? I will remove the first name and I will just rename that function. I don't need. So the switching node, a switching node. Implementation, select or add inductor to switch node and output capacitor. A little bit copy paste maybe, but sometimes you're more likely to look back at the entire documentation rather than pulling up the old datasheet, which you can, but then you have it here, and maybe it sits a little bit better in your head as well. Right. Okay, continuing. So we set it to low. Actually, we're at power good. Let's see. It's high is equal to V out ready. Low, V out below nominal regulation. So when the output is high, V out is ready. Low, it's below nominal regulation. It's open drain output, so it requires a pull-up resistor, which is this one, basically. Right, anything else to write here? V out is high when no, I'll just copy paste again. High equals V out ready, low equals V out below regulation or nominal regulation. It might seem a bit tedious to do it this way, but it makes you remember. At least it's what I like to think. The feedback, so what do we do with that? We connect feedback to ground. Connected feedback to ground. We use fixed voltage version. Ground, don't need additional comments on that. Switching frequency select. Pull to ground, meaning we have 0.5 megahertz selected. Output voltage scaling. Low equals nominal, high nominal plus 5%. So I think we tied it to ground. So we have nominal voltage scaling. Pull to ground, meaning we have nominal voltage scaling. And maybe I'll put a question mark on that. Since what does that really entail? That's what I'm curious about, at least. So I don't just do, like, if you wanted to select either one, you wouldn't just do it without understanding why. So I put a question mark on it just to verify that I understand what does it mean to pull it low. Soft start tracking pin input. So def is output voltage scaling. Didn't really explain that so well, maybe. Output voltage scaling is def. Soft start tracking pin. An external capacitor connected to this pin sets the internal voltage reference rise time. It can be used for tracking and sequencing. That's also an input. Soft start tracking pin. So what we did was follow the typical application. And connect a 3U3 farad or 3.3 microfarad capacitor between this pin and ground. Connected to this pin to set the internal voltage reference rise time. Internal voltage reference rise time. Used for tracking and sequencing. Okay, I need to put on word wrap. Hold on. You also see what I'm doing right here. Actually, I could do like this. So, perfect. Welcome to the stream. How are you doing? Okay, so this is what I'm doing. I'm basically going through all the pins, understanding what I'm doing in the actual schematic, why I'm connecting these pins to the different components, or why am I connecting VOS to the output. Is there options? Because that's a lot of what pins on an IC is about as well. It's configuration, setting it to do something. This chip works in a certain way, and we're just following a design document basically on how to work with it. So we're down at VIN. VIN, that's 10, and then you also have PVIN 11 and 12. but we don't have that on our component. Actually, I should I even look at this one? Do we even have the 16 pin one? I think we do actually, but supply connect to the same sources. Even supply voltage for control circuitry, supply voltage for power stage. Anyways, let's not worry about that right now. We know what this is. It's an input and it's the supply voltage. We don't have to differentiate between control circuitry and power stage right now, at least. Keep it simple. Implementation. Yeah, oh, we don't need to write anything. Power ground. Must be connected directly to the exposed thermal pad and common ground planes. Enable. Enable input high, it's enabled, low, it's disabled. Enable. And connected to LIN. So at least we can go back and on this chip, look at what we did. So this, make it a bit nice, light blue, project, light red. And then I can go and switch between this document and whatever I'm doing. In a data sheet, for example, looking through, okay, here it says something, and I select the appropriate component, and I document it also in this block implementation template. Lack of a better word at the moment. Yeah, let's keep it like that for now. So now we're here again, and I will look a bit more through the datasheet. See what else here is applicable for us. just looking through if there's something here I need. Voltage programming. Okay. So if we connect it to ground, we get the V out, so 5 volt. While if we set it to 1, this is the voltage output scaling. We get an additional 5%. I never seen that before and know which case you're doing that. So I'm gonna leave it as is. So what I mean is I leave it connected to ground. So we just get the 5 volt output. Would be interesting though, as an example, test by also pulling it high. So that could be interesting to have maybe a jumper here like this. What is it called? Where you can select either connected to ground or let's see, what's its 5%? Yeah, anyways, let's continue looking through. Based on direct control with seamless transition. So here's the functional block diagram. This is a control logic. Soft start, thermal shutdown, under voltage LO or UVLO. So under voltage lockout. So when the voltage drops below the input, the minimum input, I guess it turns off. Right. Power control. So this is So this is the one we're looking at. Fixed output. And here we have it explained. When enable is set high, the device starts operation. Oops. Oh. Oh. Soft start controls the output voltage slope during startup. So there's a delay, 50 microseconds, and V out rises with a slope controlled by an external capacitor to the SSTR pin. So that's this one. So this sets the rise time, I guess. Using a very small capacitor or leaving SSTR pin unconnected provides fastest startup behavior. There is no theoretical limit for the longest startup. Just gotta eat some grapes. If not used, the power ground pin should be connected to ground, but maybe left floating. Has a built-in power good function to indicate whether the output voltage has reached its appropriate level or not. So the point is here that from this point, we can start another sequence, I guess, or power up something else, or, you know, the MCU or whatever can wait for this power good signal before it does any processing. So here I will actually use my what happened to my document? Here it is. Here I can that I don't need. So what I've implemented is 100k resistor code to be out. Currently, the signal is unused. Yeah, I'll make this red. So we use it, but we don't actually use it to power something else. So we have it implemented at least. We don't have it left floating or whatever. It needs this pull-up resistor in order to work, is my understanding. That requires a pull-up resistor to any voltage below 7 volts. It can sink 2 milliampere of current to maintain its specified logic low level. This high impedance when the device is turned off to do this. Resistor is disconnected if the pin is set high. So this one we're not using the def, the voltage scaling. And so that's everything that is. So we know why. It's pulled to ground, we have nominal voltage scaling. So now at the frequency selection, it's managed to start with frequency select low to limit inrush current, which can be done by connecting the pin to V out, or wait, what? Frequency selection. That's this one. Low. Set it to low to limit the inrush current, which can be done by connecting the pin to V out, or power good, running with lower frequency, a higher efficiency, but also higher output voltage ripple is achieved. Pull low for high frequency operation 2.5. To get low ripple full output current at the lower switching frequency, it's recommended to use an inductor of at least 2.2 microhenry. The switching frequency can be changed during operation if needed. Pull down resistor of about 400 kilo ohm is internally connected to the pin, acting the same way as the def pin. See above. It is mandatory to start with frequency selection pin equal low to limit inrush current, which can be done by connecting the V out or power ground. Right, I think actually question is, what does it matter? Wait. TPS DC-DC 5 volt power ground. Oh. DC-DC power ground. most likely only have these two, right? And we should remember to put on labels, actually. It's important on the nets. Here we have 5 volt, here we have ground, here. This is also 5 volt, DC-DC, power ground, DC power ground. This a little bit over, so. SS is DC SS. Move it over a little bit, so. And then the input here. Okay, all labels is in place. N 3.3 nano farad. Pull to ground is not correct. Set to outputs. Meaning we have 2.5 megahertz switching frequency. Switching frequency selected. Yes. It will be so rewarding when we have everything in place here. Knowing everything what this whole block does, and know for a fact that it will work. Okay. It is recommended to use an inductor of at least 2.2 microhenry. So at least 2.2 micro. So we put that, and we also do we comment somewhere about this? Yeah, how are you doing? Welcome to the stream. Welcome. We're doing electronics. We're working on electronics from concept to production. We're currently doing power management, and more specifically a DC-DC buck converter. It takes 12 volt and converts it to 5 volts. Okay, what else do I need to document here now? Yeah, let's continue reading through. Yeah, I documented that we connect to the power good outputs, so that we select 2.5 megahertz switching frequency. And now for the under voltage lockout. If the input voltage drops, do we need to do anything here? Miss operation of the device by switching off both the power FETs. It's typically set to 2.7 volts. So it trips if it goes below that. Thermal junction. Need to think about it. Device functional modes. Pulse width modulation operation operates with a PWM in continuous conduction mode with a nominal switching frequency of 2.5 MHz or 1.25 MHz selectable with the SW pin. Frequency variation in control depends on V in, V out, and inductance. Device operates in PWM mode. As long as the output current is higher, half the ripple current of the inductor. Just gotta eat some grapes now and then. Now and again. Welcome to the stream. Okay, I kind of want to go through these things. I kind of want to go through these things also later. They're not really directly applicable for what we're doing right now. So 100 duty cycle operation, for instance. Increases as the input voltage comes close to the output voltage. In this case, the device starts 100% duty cycle. Current limit and short circuit protection. So it has that against heavy load and short circuit events. That's good. And this is more maybe, so sorry for my babbling here, but I'm really looking into a good way to do design. So a good way to document what we're doing. So power management block, for instance, I want to make a design template of each functionality block. And for example, the power management, we said we want overcurrent protection, reverse polarity protection, surge ESD protection. A regulator, we didn't specify anything. So on this point, we didn't specify if we wanted protection on the output here. So for instance, are we driving anything else with this 5-volt output? Do we want some type of overcurrents, short circuit protection on this output? If there's any load connected to this that has a short, then we have the protection for it. But do we need it? And that's what I want to document in the future. Make a design template asking ourselves, do we need protection on the 5-volt output? For example, we add a rail, what type of protection do we need on that rail? And is that the right way to think? All very good questions by yours truly. And that's what we're answering on this channel. We're really trying to understand our electronics better, making or creating a type of design flow where we can build electronics all the way from concept to production and really have confidence in what we're building and ordering with no doubt that it's going to work. Of course, we can always make mistakes, but if we're following a tried and tested, or at least thought out, design flow, way of working, there's a bigger chance we will succeed. So it has current limit and short circuit protection. It just explains how it works, more or less. Then we're down to the application and implementation. It needs a minimum amount of external components apart from the LC output filter and the input capacitor. Only the det variant needs an additional resistor or divider circuit, voltage divider, to set the output voltage. We don't need that, so we'll skip it. Design requirements. Yeah, there you go. I mean, that's one. Programming the outputs, don't really need it. External component selection. What's going on here? Recommended LC output filter combination. So we needed at least 2.2 microhenry. Effective capacitance was considered to vary by +20 and -50. So that's DC biasing then. So smaller capacitance equals smaller voltage ripple, question mark. Relationship between capacitance and ripple voltage is inversely proportional. A larger capacitance results in smaller voltage ripple, and a smaller capacitance results in a larger ripple. Right. This is the recommended. The LC combination is the standard value and recommended for most applications, which is 2.2 and 22 microfarad. So we will go with that. We will go with that. I wonder if I should also do the selection of components here. Selection of components. Where I should document that. So let's annotate for now. So C1, C2, R1, L1, C4. Yeah, that works. That works. So selection of components. Type. Name. Capacitor. C1. C2. C3. Inductor. L1. R1, C4 function. Input capacitors, capacitor C3, which is the set rise time. Output capacitor, inductor or switch node, inductor, R1, resistor, power good. Enables power good. Enables power good, which it does. So yeah, this is all the external components. External components. Make that orange. Info or information. So what information do we have here? So the output LC filter, we want a 2.2 microfarad. An output capacitor, oh, microhenry, sorry. Here we want a 2.2 microfarads. So this combination is recommended. Comments. Recommended by datasheet standard config. Standard configuration. You can always tweak that, right? So, oops. Like that. in configuration. So again, I just want to, whoops, CDAC package, put it up there. External component selection. So again, we want to be list of inductors. We want to be entirely sure so these are recommended for use. The 2.2 here, 3.8. That's too much. You can go for this one instead. A bit smaller. So that's this one. 1212 package. Oh, it's actually, wait, I will change to English. So it's end of life, actually. Schedule for obsolescence, and will be discontinued by the manufacturer. 1212 package. Maybe there's an alternative. So let's just do like this. Then we see if we find one with similar characteristics. So we want power inductor, inductance 1.2. No, it should be 2.2, but and let's, we don't have to select Vishay maybe, but inductance should be 2.2 micro Henry. Tolerance 20. Maximum DC current 5. Don't really need maximum DC current 5 though. Or do we need to over dimension the current side? Alright. Because if we're drawing more than saturation current, let's say 4 amps then maybe. Or I think we can say 3 now. Then we got 34 types, and if it's also automotive, we got 6. And then maybe we should tick off that it's in stock, active, and RoHS compliant. Then we got 3. We got one from Shay here. Similar package, a bit bigger. 1616. So this is one of our options. It's quite expensive though. Maybe it's a little bit overkill. What else can we skip here? Skip the saturation current, maybe. So maximum DC current. Maximum DC current. Should be 3 amps. Nah. Here we got 318. Hold on. So this can. So it has a 3 amp output. And this thing is obsolete. No, not that one, but the other one. Excellent DC-DC energy storage up to 1 megahertz to 2 megahertz. Does that mean it's not really the best for our device or our application? Am I in the way here? Should I move a bit further down maybe? that occurred. Oh, yeah. Max plus. Okay. Okay, maybe for the time being, we just select this component. Hold on. I guess it's really obsolete, huh? Let's see here. This is not the same component. This is a 1 microhenry. .2. That's that one. Hold on. Is it this one? No, high power choke. Low DCR. So I'll be set 11. Beat set 11. Was it also 3 amps? 2.2. 3.3. Okay. Not for new designs. Alternative device is this one. So let's see, inductance 2.2, so this one. Saturation current 5.3, 30% drop. What drop? So 1212 package code, inductance 2.2. Energy storage for low profile DC converters. Okay, let's go for this one. So that would be 2.2, this one. 2.2. Selected component. And this maybe needs a little bit more work. Like how I come to that conclusion that I just select that. But now I'm eager. I'm eager to get started a little bit too. So basically, we follow the recommendation of the datasheet of selecting this component. There's nothing more to it, really. For the time being. Of course, we can tweak that and select a better inductor, and it's etc. I will copy this though. block implementation. So, datasheet. Come on now. So, okay. So that's one. There's one component selected at least. We're one step closer. The architecture of the chip allows to use from tiny ceramic output capacitors with low equivalent series resistance. These capacitors provide low output voltage ripple and are recommended to keep its low resistance up to high frequencies and to get narrow capacitance variation with temperature. It is recommended to use XZR or X5R dielectric. Using a higher value can have some advantages like voltage ripple, smaller voltage ripple, and tighter DC output accuracy. Power save mode. Right. So we can go back to passive components, and then we look into selecting that output capacitor with low ESR. Capacitors. Uh, 22 micro. Voltage rating then on the output can be 6.3. We check what we get. Should at least have this dielectric tolerance, I'm not sure. Can do the smallest and 0.805. Should also be, does it have to be automotive? Can do this one. It's a class 2, 0.805. So what I'm the most interested in, well, footprint. So this one was 1212. This one was here. Copy the component 0.805. We got the value. And I need to be careful here so I don't just add and add and add this information, because it can be too much too. Also do word wrap here. Oops. Didn't exactly select low ESR. Okay, what else am I really interested in here? I mean, there's a lot, right? The voltage rating, tolerance, dielectric. Information. I will put everything here. And then I take away this, take away that. Wait, so it's 2.22 microfarad. It's X or 7X, no, X7R. It is 6.3 VDC 0805. What else is good? 20% tolerance. 20%. Ugh, this is a horrible data sheet. I don't like this. Okay. And then we have this one. I will just write the most important information. Which is the package, of course. 1212. Inductance DCR. Like in this case, we don't have any other options than this. Hmm. Ba-da-da-da. Soft start capacitor, inductor selection, output capacitor, input capacitor. A low ESR multilayer ceramic capacitor is recommended. Best filtering should be placed between. It is required. So 110 microfarad and 100 nanofarad then. So that is this one and this one. So we can actually increase the capacitance here to have a smaller current ripple. The input capacitor buffers the input voltage of transient events and also decouples the converter from the supply. A low ESR multilayer ceramic capacitor is recommended for filtering. It should be placed between, but it's not required. Yeah. Okay. Let's go back to here. And then we can drop that one and drop the capacitance. We need 110 microfarad. And now the voltage should be maybe at least 16. We have the 12 volt output. But maybe we should do 23, no, 25 and up, I mean. Because 16 is below the DC-DC. So the DC-DC can take 17 on the input. And this will clamp it to that as well, I think. The specific component that we selected. Up to at least that, I think, or even more. I think maybe it's best that we select 25 on these, so they're above what the input of this DC-DC. Because if it really was 16 max here, then I wouldn't have to select a DC-DC higher. Right, I could also select it lower. Maybe. Let's go with 25. 25. Did I not select 10 micro? And then in stock, active, and ROHS compliant. Samsung, they have a lot. TMK. Samsung, Murata. What's up with this? I want it. There you go. For instance, this one, 10% tolerance, 1206, 1206. It's bigger than the other one, the 0805, the 22 microfarad one. Why are they so? Oh yeah, of course, because it's the voltage rating. Okay, then 1206 is not too bad then. Let's do that one. And I should change the currency to US dollars. 0.3 for 1. So it's automotive, 1206. Yeah, this is all we need. Let's do that one. So that's the first input capacitor. So C1, which was the 10 microfarad. It's also X7R. It's 25 VDC. 10% and 1206 package. Here I put that. Then the datasheet is here. Let's just give the mouser link. It's better. We'll figure it out anyways, which one is which. Okay. What else? Where are we? We need a 0.1. So we need same characteristics, basically. Just not 10 microfarad. We need 0.1 or 100. 0.1. This one. And here's a way smaller packet, 0402, 0603. I think we do that one. Yeah, we can copy this actually. It's quicker to do it like that. So C3 and then the resistor, and then we're good to go. Then we're good to go with that entire circuit. And now we can be very confident actually in what we have done. Comment, select a component. Want to add some price or some costs eventually to all of these. So we can, this is more, actually should be more included in a joint boom list. But in the end, we can always just go over and copy paste from the individual block implementation. But soon I need to end the stream very, very soon. So I've been streaming for about 2 hours, working on electronics from concept to production. Let's see if we can just get out one more capacitor. It's already been specified. Let's see, output filter. No. System example, LED power supply. Oh, okay. Interesting. And here layout guidelines. Cool, cool. Power supply recommendations. But it's not too complex. Quite simple actually, I think. Without sounding too cocky. Okay, where's this 3.3? 3.3 nanofarad. 3.3 nanofarad. Where is it? So C1 and C7, also 25, 0603. That's the same as I selected. C1 is a 10, also 25, 12, 10. 12, 10. Anyways, C5, also 25. Okay. We can go back here at least and select one with a capacitance of 3.3 picofarad, 3.3 nanofarad, and then check what we have here. 20%. TDK 0201, 0402, 0201. Did they select 0603? I also kind of want to just select a little bit bigger package for now. 0603. Let's do 0603. So yeah, let's do that one. Also from Murata. Then we'll copy this here. And plug it in to our template. So here, this. And then the resistor, check what it says here. Just a standard 100K 0603. So let's just be a little bit quick about it right now. And add this, we still haven't selected, but we should select 10603, 1/16, 1%. Let's go to passive components, do resistor, SMD, and 100K, 100K, 100 kilo ohm. power rating. So 5 divided by 100. That's 0.05 milliamps squared times 5 is 125 milliwatt. So this is kind of a little bit okay. Oops. We only found one left. Okay, that's not correct. Power rating can be this one. 1/8. So an inch 0603. Then we got 72 to select from. Is a little bit too let's just go for this one. It's 100 kilo ohms, power rating 125 milliwatts, 1%, 75 volt rating. Okay, that's a bit overkill. Maybe. See if I can go back here and hundred, 1/10. Does it matter though with the voltage rating? Is that one? Yeah, I guess it doesn't matter so much. Let's go back and we select 1/8 again. Lots in stock of this one. Let's go with that one. Package is 0603. Okay, that's it. Then we selected every component that we needed. So all the external components for this buck converter. This buck converter, to be precise, so we followed the data sheet more or less and followed their recommendations. And then selected, of course, the appropriate components based on what we know. So voltage ratings taken into account, the values, so capacitance value, resistor value, inductor value, all recommended, and then selected by us. And documented in this block implementation template. I kind of like this way of working where you split it up. So looking at this block then, regulation or regulator, in the power management block that we have. So we take this part, we focus entirely on that. And this is what we get. Documentation ready to do design. So now we can plot in, we can select footprints, everything that we need. And then we can do layout. But of course, we're not there yet. This is just one block out of many. Not that many, but we're not done with the schematics. But at least we're done with selecting the components of this part right here. So then we'll, next time, get this done. Or at least a polyfuse, see if we can find a appropriate component for that. We have already documented these components for that block. So this one, except for the connectors. So maybe we should look into the connectors next time. Okay, that's it for today. Thank you so much for watching this stream, this episode 3 of the multi-node LIN network. Yeah, not much more to say, really, than keep working hard. We'll get there. We'll get to a fully fledged automotive LIN network that we will get working. We will design it, we'll program it, and we will test it. So thank you for watching. If you like this content, please hit the subscribe button and also give me a thumbs up. Really appreciate that. Let's build this community and reach for the stars. Thank you for watching.